Hello everyone. Once again, welcome back to a big O series in our computer science world. So today we will first go through a very short recap of what we have learned so far, and then we will continue with the next part on this series. Okay. So with that, let's get started. So as I have previously mentioned in earlier parts as well, so to prepare this playlist on big O notation, I have gone through technical blogs on internet, and I have also referred Cracking the Coding Interview 6th edition book, which is a really a nice book to learn the fundamentals and working on the problems. As well, I have taken help from generative AI tools like ChatGPT, Gemini, and Claude to build my understanding and then draft or create this useful concept. So this is basically the part 5 on the Big O playlist, but we started with part 1 wherein we uh, started with the introduction for the Big O. What is Big O? Big O is basically the notation or a metric or a language which is used to analyze the efficiency or runtime of a given algorithm. So algorithm is nothing but a code which can be written in any programming language, and we would like to evaluate when the program will run or when the algorithm will run, how it is going to perform in terms of the size of the input. So to basically represent its runtime or efficiency, we use this big O notation. So even before starting this time complexity thing, so we can actually talk about big O, big omega, and big theta very brief. So basically, uh, it describes the like the upper bound or lower bound on the runtime. So big O describes an upper bound on the runtime. What it means is like an algorithm can take maximum of this much amount of time, right? So for example, if we say if an algorithm is taking order of n time, then what it means is that where n is the size of the input, then it means that it can never uh, it the maximum runtime or the upper bound on the runtime is directly proportional to n, right? So that is the upper bound. So big O describes an upper bound on the runtime. Likewise, big omega describes the lower bound on the runtime. And then big theta is actually the tight bound on the runtime. And that is what we would like to use big O by determining the tightest bound on the runtime. Okay. So anytime you would like to analyze the efficiency of a given algorithm, then just keep in mind that always try to think the tightest bound on the runtime. Okay. Now, in terms of time complexity. So time complexity is closely related to the runtime of an algorithm. So how much time our algorithm is going to take with given input of n, right? So there are few very commonly seen complexities time complexities, and even you will encounter the same common complexities in whatever code you write or you see. So for example, ON is a linear complexity. Likewise, O1 is constant time. So constant time means it doesn't depend on the size of the input. It is usually doing something a fixed number of times, something like that. And then we say, though later we will cover the ordering, which one is more efficient. But essentially, we say that how big the constant is and how slow the linear increase is, linear will always surpass the constant. So it means that constant time complexity is always better than linear time, right? Then there are few other runtime complexities as well, like log n square to keep 2 raised to the power n square root of n, like that. And it also like logically makes sense that we can say that there is no fixed list of possible runtimes. And our runtime or time complexity or space complexity, which we will talk about later. So we can have multiple variables while defining the complexity in big O notation, right? We can have multiplication, we can have addition, we can have multiple variables like that. Then in part 2, we covered the best case, worst case, and expected case scenarios, right? So it basically mostly correlates to how our input data is. So for example, in the best case scenario, so for example, if we have an algorithm, right, find number, which accepts an array, and then as well the number which we have to find in that array. It takes two parameters, right? And then the logic of find number method is linear search. So it will iterate through all the numbers at each index one by one, and it will match if the given number is same as what we have at the current index of the array. If yes, then return, otherwise keep going, right? And if at the end we have iterated through all the elements in given array and we have not found the number, then we just return -1. So in that way, best case complexity will be that my array and my number is such that it is at the very first index of the given array. So that is the best case complexity, right? It will be very quick. The execution or the runtime will be very quick. Likewise, the worst case is when it's not able to find the number in the given array. So that is the worst case complexity, which is directly proportional to the number of elements we have in the array. And then the expected case is average case. Average case is the case which usually happens on a random day, right? So probably the array and the number will be such that on an average basis that the number will be somewhere in the middle of the array. So in that respect, it's technically its complexity is n by 2, but we drop the constants, so it is always like order of n in this particular algorithm. So overall, what we are trying to say is that the best case, worst case, and average case complexities depends on the particular inputs or the particular scenarios. Then in part 3, we talk about space complexity, which is a parallel concept to the time complexity, right? So if I go back to take the example of this find number algorithm, so in this, uh, one aspect is how much time this algorithm is going to take in terms of input, right? And the second aspect is how much space or memory it is going to consume. So somewhere in some algorithms, for example, you will see that we are creating an array of the size as the input array. So it means that it will be using more memory, right? And in some algorithms, you will see that we are just defining few variables and that's it. We are not creating a huge memory or space. Our program doesn't need more space, huge memory and space. In that way, its space complexity is something like constant. So that is what the space complexity is all about, right? Then we saw some recursive calls examples to discuss about the time and space complexity. And then we have some like points which we can remember in when we are evaluating space or time complexity. So first one is like we can drop the constants when determining complexity. So if at some place you see order of actual complexity technically is coming as order of 2n, then we can just say order of n. Likewise, if it's order of n by 2, then it's order of n. Likewise, if it's coming order of n plus 3, then it's order of n, right? So we can drop the constants thing. And likewise, the another point to keep in mind when determining the complexity is dropping the non-dominant terms. So what does it mean is like if we have found the complexity like n square plus n, so we can just drop the non-dominant term, which is n in this case. So we can say n square is its complexity. So we can always focus on the major term in this complexity. And why? Because initially we talked about the tightest bound on the runtime. So we always look for the tightest bound. And tightest bound will be one where where we are considering the major term, not the minor one. Or we can say dominant term and not the non-dominant term. So we can drop non-dominant term while determining the complexity. In part 4, we just uh, gone through like the most commonly used complexities and how they are better, right? So for example, here you will see constant time is the most efficient complexity. Then comes order of log n, then comes order of square root of n, then comes order of n, then comes order of n log n, then comes order of n square, then comes order of 2 to the power n, and then comes order of factorial n. So it's not that you have to memorize this, and even you can figure it out yourself by simple maths. So for example, if n is 8, then log n is 3, right? So it means log n is lesser than n. Order of log n is lesser than order of n. So it is more efficient, right? But if we understand like, yeah, there is some better complexities and we have written a program where the complexity is coming as order of n, then we may try to optimize that algorithm to make it to order of log n, right? So for example, a scenario is we have taken is binary search, right? So if we know, if we have to write an algorithm wherein we have given an array, sorted array, and we have given a number, which number, like the number which we wanted to find in that array, then rather than doing the linear search, we can go for the binary search. Because in linear search, the complexity is order of n, Whereas binary search, the complexity is order of log n, and we know log n is better than order of n. So knowing the ordering of these most commonly used complexities always helps. Okay. Then comes basically the steps in a given algorithm. So I guess sometimes we get, I think not everybody, but like I used to get confused whether I should add the complexities which is coming out in a single algorithm. So basically what I mean to say is that, so in a given algorithm or in a given code or in a given function, we will be doing multiple steps sometimes, right? So now for each step, there could be a different complexity. Now, sometimes a confusion might occur whether should we add the complexities of those two different steps or should we multiply them, right? So the general principle which we can apply in such cases is that if we are doing steps independently, wherein the complexity is coming different for each step, then we can just add those complexities. So for example, in this first scenario, what we are doing is we are given two arrays and we are first doing a for loop on array A and then we are doing for loop on array B. Now we do not know the length of array A and B. So we can simply assume, let's say the array A length is A and array B length is B. So in that case, my complexity is going to be order of A plus B. Whereas if I have a different algorithm where I have two arrays as input A and B of length A and B, in which I am doing nested for loop, outer for loop iterates for entire all the elements in array A, and then in inner for loop it iterates through uh, each element in array B. So essentially for each element in array A, I am iterating the for loop for array B for each element in array A. So it means overall how many times, how many steps will be done in this algorithm is A times B, right? So the complexity is going to be order of A times B. So overall, if there is some kind of dependency, then it is a candidate for multiplication. If it is independent steps in the algorithm, then it's addition. Then later on, we talked about the amortized time. So amortized time was like average time, average cost over a long period of time. So herein we talked about the uh, array list, right? Which is a dynamically resizing array. So we found from the calculation that if we want to determine the runtime of insertion in array list, so that comes out as order of one amortized cost. So I will not go through that example again. So you can basically refer to which part it was, part 4, to go through that example. But we found that if we want to determine the runtime of insertion in array list, so that it was coming out as order of 1. So now let's talk about part 5. So in part 5, first we have is order of log and time complexity, right? So we do not need to memorize this. So today we will be going through how this log and complexity comes from, right? From where it comes from. So if you have given an algorithm, then I think understanding where it comes from can help you to see if a given algorithm is running in log and time or not, right? So log and time complexity. So basically, we can think of binary search. So what is binary search? So in binary search, it's sorted array. So we are usually given an array which is sorted and we have to find a number. So we are also given the number as well, right? So maybe what we can do here is, so we can first go through the example I have here, right? So what we have here is, so I will just do, I think this should be fine to get visible properly. So let's say we are given an array. So this is a sorted array 1, 2, 3, 4, 5, 6, and we have to find 6, right? So what we do in binary search is, so uh, and 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 remember to uh, so one aspect of understanding it is keeping in mind how the linear search works, right? So in linear search, if we have to do the same thing, so eventually we iterate, or we iterate through all the elements in this array one by one, right? And we check at each index if the number is matching the given number. So if it matches, then we return its index, or whatever we want to return, true or false, so we return. Otherwise we keep going, and finally we end here. And if we don't found the number, given number, then we just come out of the loop and return -1, for example. So in linear search, we are iterating through each element. We have to evaluate each index and what is the element here, and then we have to see if that element at that index is equal to the given number or not, right? So we are evaluating each element in given array in case of linear search, and that's why the complexity over there is order of n. N is the size of the input, right? Now in binary search, it, as the name suggests, it's binary. Binary is 2, right? So we basically, so but the prerequisite for binary search is the array, given array should be sorted. So what we are doing is, let's say in the first step, we know my lower bound is 0 and my upper bound is 5. So we find the mid index of these two. So 0 plus 5 divided by 2, which comes out to 2, right? So now we know from this given array that my mid position is 2. So I will check whether at index 2, what is my number? It is 3, right? So is this number matching my given number 6? No, it's not matching. So this is step 1, right? So we again, because we haven't found the number yet, so what we do is, here comes the binary thing. So here we know that my number 6 is going to be in the upper half, right? Because it's sorted array. So 6 is going to be in upper half, because at mid position it's 3 and 6 is greater than 3. So it's going to be in the right half of this array. So what we have done here is, if you carefully look at this, So we have basically shrink the size. So we have broken the array into two parts, and we are ignoring the first or left portion of that array. Why? Because we know that number 6 is going to be in the right hand side of the array, right? So now my my upper bound is still the same, but my lower bound is now the mid position plus 1, right? So I am saying 3 plus 5 divided by 2. So that is my second step. So which comes out as 4, right? So now I go to index 4, which is number is 5, it's not 6. So again, we have to shrink the array, right? So we are at position 4, and we know that the number at 4 position is 5, and my original number to find is 6. So it's going to be in the right hand side, right? So now my lower bound is this mid position plus 1, so it's 5. So my upper bound is 5 and my lower bound is 5. So it means I am at the last index of the array. So if I find it here, then it's fine. If I don't find it here, then I will return -1, because now I cannot go any further, right? So we again evaluate. My lower bound is 5, my upper bound is 5. So 5 plus 5 is 5. 5 plus 5 is 10. 10 divided by 2 is 5. So at index 5, the number is matching with the given number, right? So if you see here, right? So if you see here, my total number count was 6. So n was 6, right? So in linear search, I evaluated all the elements in this array. But here, if you see, so I have just did 3 steps. So first I looked at position 2, then I looked at position 4, and then I looked at position 5. So just 3 steps, right? So so overall, overall, we are saying that uh, so what we have done here, right? So in each step, my input size is half of the previous one, right? So initially it was n. Now in the next step, it's n by 2. Now it's n by 4. And eventually there will be just one step. So after that, I cannot go any further. All right. So now if I want to evaluate or generalize how much will be the time complexity of binary search for size, input size of n. So what I have to measure is or calculate is how many steps I am doing. So initially there were n numbers, then it was n by 2, then it was n by 4, and eventually just 1. So let's say, so basically now if you see here, right? So it's n by 2 raised to the power 0, n by 2 raised to the power 1, like that, right? So here, let's say these are the total k steps or k terms. So 1 is going to be my kth term, right? So I am saying my kth term is n by 2 raised to the power k minus 1. So we are saying that we have to find how many steps we are doing here. So we cannot count it, right? So let's say it's 1, 2, 3, like that. So let's say there are k steps, right? So this is my kth step, right? So I am saying my kth term is 1. But then how I can also write 1 like this. So my first term is n by 2 raised to the power 0. Second term is n by 2 raised to the power 1. Third term is n by 2 raised to the power 2. So this is my third term. So power here is 1 less. Third, 3 minus 1, 2. Likewise, if I am saying that these are the k terms and this is the kth term, then this is going to be my n by 2 raised to the power k minus 1 based on this understanding. So that's how I have written this. So kth term is n by 2 raised to the power k minus 1. But now I know I can say 1 is equal to n by 2 raised to the power k minus 1. So from this maths, we can say 2 raised to the power k minus 1 is equal to n. And if I do it further, so 2 raised to the power k is equal to 2n. And if I take the log on both sides, so k is equal to log of 2n. And then we can drop the constants. So my complexity is log n, right? So overall, uh, we were given n numbers and we were able to find whether the number exists in the array in binary search in log n time. I think I will take one more example. So basically now let's go back to what we said here. So log n time complexity, you can think of binary search where we find element in sorted array using binary search. Then it's just the same calculation here, right? So it is just how we are evaluating the time complexity, which is coming as log n. So I can take another example very quickly. So let's say this time we are given 8 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. Right. So again, we want to do the binary search. And let's say this time we have to find the number 1 is there or not. So let's do this run as well. So step 1, 0 plus 7 divided by 2, 7 divided by 2, 3. Array 3 is 4 and it is not equal to 1. So we move on to next step in which we know that our number can be in this first half, not the second half. So this time uh, we shrink it from the right hand side. So my lower bound is still 0. My upper bound is 2. So I do 0 plus 2 by 2, which is 1. Array of 1 is 2 and it's not equal to 1. So again, I am at this position and I know it is not equal to given number 1, but so my number is going to be in this range. So again, I reduce the lower upper bound. So this time I say in step 3, it's 0 plus 0. So earlier it was position 1, now it will be 0. So 0 plus 0 divided by 2 is 0. And then we know that array 0 is 1, which is equivalent to 1. So basically, we found the number at index 0. So how many steps we took? So the total numbers were 8, and we were able to do it in just 3 steps, in 3 evaluations, right? And if you calculate log n, so log n is log 8, and 8 can be written as 2 raised to the power 3. So log 2 raised to the power 3 comes to 3, right? And this is what we can see. So overall, 3 steps for 8 numbers in the array, right? So every time you basically encounter something like we are shrinking, we are just doing something in first half, and then half of that half of that half, like that. So it, you can think of log n time. Okay. Then the next one is recursive complexity. So this is the last part, or this is the last portion of this part 5 series, this part 5 video. So let's go through this one as well. So recursive recursive code is actually, though I will explain many examples in later part of this series, but for now let's get the understanding of recursive code complexity, right? So let's say there is a method in which what we are doing is it takes input n, and then in the logic it will check if my input is less equal to 1, then return 1. If not, return m of n minus 1 plus m of n minus 1. So here we are, so this is an example of a recursive call. So the upper part is just fine. So we have a test class in which we have a main method. So we know that in Java, when we will call this, or we will run this Java program, Java test, then the program will start executing from main, and it will call this method m with input as 5. So this method is going to run based on this input value of 5. So here what we want to do is we want to evaluate the time complexity or the runtime of this method m, right? It's not about this one. It's very quick. The upper part is just the execution. So we are calling this algorithm with input value of 5. So we want to determine the time complexity or the runtime of this m method. So every time if you want to determine the time complexity or the runtime, actually what we have to do is we have to see how many steps we are doing, right, in that method. And we have to generalize that thing in terms of n, in terms of input, right? So in this case, what I am doing, so we can go through. So first of all, recursive call is when a function calls itself. So you can see here that in the logic, it calls itself with a value less than 1 of itself, right? So I am initially calling with it with n, and then in this logic it calls itself with n minus 1, right? And then eventually it, as soon as it will see the value as 1 of n, then it will just return it from there. So it's going deep and deep and deep, and then coming out, and finally it will return a value which we will print in the main method, right? So in this case, so in this case, the very first thing is outprint. So it's just the constant time, right? It doesn't depend on anything. So we are just printing is the value of n. Then in the if block, where we are checking if my value is equal to less equal to 1, then return 1. So this is also, if you will see, so this is a constant time kind of thing. We are just evaluating value of n and returning immediately, right? Now the main thing is this return statement where we call the function itself with n minus 1 plus n minus 1. So if we want to determine in terms of n how many steps we are doing in this, so we have to focus on these two parts, right? Because they are deeply calling the same method again and again. So we have to see how many times we are calling this method again and again. So that is going to be my time complexity. So if I have a look at this, so I have tried to uh, picturize this so that it can be understood easily. So let's say if it was 5, right? So maybe what I can do is, or maybe, I don't know. So I can just uh, take this screenshot here, copy this, and then paste it here. Oops. Oh my God, something got hang on. So I know this picture is a bit, I wanted to put a code as well side by side so that you can understand it. But what we are doing here is, uh, so we have initially n is equal to 5, for example. So what will happen is n is not equal to 1, less equal to 1. So it will not go inside if block. So what it will do is, in general, it will call this 4, and then later part, it will also call one more time this 4. So for n is equal to 5, my function, same function will be called for value 4 two times, right? Again, when 4, it will be called two times for value of 3. Likewise here. Then for 3, it will be called again two times for each 3, right? And then for each 2, it will be called two times. Because here is the case, it will keep going deep unless n is 1. Because when n is 1, then it will stop. So it means that for each 2, it will do 1 two times, right? So how many, if we closely monitor this, so at 1, it will just return it back, right? And when it will return back, it will try to resolve itself, right? So from 5, it goes till 1, and then from 1, it will go up to get resolved. So from top to bottom and then bottom to top, right? So that is what we are doing. So it first goes deep one by one, and then it goes from deep to up again to resolve. But the important thing is how many times this method will run, will be called for n is equal to 5 is this step plus this step, these two steps, 1 plus 2 plus 4 plus 8 plus 16, right? Because for each value of n, it will further go 2 times. So until it gets 1. So for 5, 2 fours, then for each 4, it will go 2 times, for 3, like that. So these are the total executions, right? If we sum this up. So 1 at level 1, then 2, then 2 raised to the power 2, then 2 raised to the power 3 plus 2 raised to the power 4. So we have to sum this up, right? Now, if we want to sum this up, so this is we can write it like this: 2 raised to the power 0 plus 2 raised to the power 1 till 2 raised to the power 4, right? And then, this is a geometric series, right? GP in short. So in GP, the formula is A into r raised to the power n minus 1 upon r minus 1. So where A is my first term, so this is 1. And then it's 2 raised to the power n. N is the number of terms in the series minus 1 divided by 2 minus 1. So because we have to count these all steps, so steps we are doing is like total steps is these steps, right? So if we want to find this sum, so this is a GP series, and from GP series it comes out 2 raised to the power n minus 1, where n is my number of nodes or number of terms in this series, right? So and we know in our case n is 5, so it's 2 raised to the power 5 minus 1, which comes out to 31. So this is with the GP series, we can get the sum, but because this is a small program, so if we individually count the steps as well, 1 plus 2 plus 4 plus 8 plus 16, so that will also come out as 31. So it means that our calculation is right. So we are calling this method 31 times, right? But if you see here, so eventually almost, if we are given n numbers, then it is coming out as 2 raised to the power n, right? So it's 2 raised to the power n minus 1, and we can drop the constant. So it is 2 raised to the power n times, roughly we can say, this recursive call is taking. So if there are 5, value of n is 5, then this function will be called 32 times or 31 times, right? So because at each step we are doing 2 branches for each value of n until n is 1. So this will be like this. So every time you see or you encounter an algorithm or a logic or a step where we are actually doing it's in 2 branches, going deep, 2 branches in each level for each node, then it will be roughly 2 raised to the power n. So I think uh, that's it. So here I have just printed out, taken the screenshot of printing out it, right? So even you can count it, but it will be roughly 31 for n is equal to 5. So I think that's it for today. Feel free to drop any comment if you have any question about it. But I will be coming up with more and more examples with different codes, different algorithms, and we will work out together. We will learn together to understand the complexity of those examples. And I guess once you basically go through all these parts in the series, then I am hoping that you will build a very good understanding of big O complexity and the different patterns which we can utilize to solve the time complexity or space complexity of a new problem. So with that, happy learning and thank you.